Imagine a world 100 million years from today. Everything we've built, our sprawling cities, our skyscrapers, our iPhones, even our very bones, has been ground down into a thin layer of dust, just a few millimeters thick, buried deep in the earth, gone without a trace. If that is our inevitable future, we have to ask, could it have been someone else's past? Forget about aliens or science fiction myths for a moment. Let's look at the hard geology. 65 million years ago, a single asteroid left a global scar of iridium. That is how the Earth remembers. So, if an industrial civilization existed long before us, if they burned fuel, altered the atmosphere, and reshaped the land, where would their chemical fingerprint be hiding beneath our feet? Tonight, we aren't hunting for ancient statues or lost ruins. We are here to decode the memory of stone to answer one haunting question. Are we truly the first to ever shape this planet? Before we go any further, let's be clear about what tonight's story is. This is not a claim that a lost civilization once ruled the Earth. It's a scientific thought experiment. We'll be asking a careful question. If an industrial civilization existed long before us, what kinds of traces could science still detect today? Throughout this journey, we'll keep a clear line. On one side are things geology and chemistry can test, measurable signals written into rock, ice, and atmosphere. On the other are ideas that remain speculative, useful for thinking, but not treated as facts. We won't confuse the two. The goal isn't to reach a conclusion, but to follow the evidence as far as it can go. And with that in mind, so let's begin with what the Earth can prove. To understand this question, we need to step outside human time. Earth is about 54 billion years old. That scale is difficult to feel, so let's put it in perspective. An average human life lasts around 80 years. Recorded human civilization goes back roughly 10,000 years. Compared to the age of the planet, those 10,000 years represent about 0.000022% of Earth's history. In geological terms, that's not an era. It's barely a moment. Earth doesn't experience time the way we do. It doesn't remember events by decades or centuries. It operates in millions and billions of years. Over those vast spans, the surface of the planet is constantly changing. Mountains rise and slowly wear away. Rivers grind rock into sediment. Oceans open, close, and shift their boundaries. And beneath it all, plate tectonics quietly recycle the crust itself. From our perspective, this looks like destruction. From Earth's perspective, it's simply how the system works. Almost everything built on the surface is temporary. Steel corrodes, concrete fractures, glass weathers and breaks apart. Even biological remains rarely survive intact beyond a few million years. What lasts is usually altered, compressed, or transformed into something else entirely. So if a technological civilization existed millions of years ago, the absence of cities or machines wouldn't be surprising. It would be expected. This is why looking for ancient ruins deep in time is the wrong approach. Geology doesn't preserve structures very well. What it preserves are changes. Changes in chemistry, changes in composition, changes that affect the planet on a broad, global scale. In that sense, Earth acts like a recycling system, breaking down physical objects, while quietly recording the effects those objects had. Time is very good at erasing shapes and forms, but it's far less effective at erasing signatures. And that's the shift in thinking this story requires. If we want to look for evidence of deep history, we can't search for what once stood above the ground. we have to look for what altered the planet itself, subtly, chemically, and in ways that could survive immense spans of time. And that brings us to one of Earth's clearest memories. 66 million years ago, something happened to this planet that changed life forever. It wasn't gradual, it wasn't subtle. A massive asteroid struck Earth, triggering what scientists call the KPG boundary. The moment when the age of dinosaurs came to an abrupt end. Entire ecosystems collapsed. Roughly 3/4 of all species disappeared. And yet, despite the violence of that day, the most important evidence it left behind is surprisingly quiet. All around the world, scientists have found the same thing. A thin layer of clay, only a few centimeters thick, buried between older rock below and younger rock above. This layer appears on every continent, in mountains, on coastlines, even deep beneath the ocean floor. What makes it remarkable isn't its thickness, it's what it contains. That clay is rich in iridium. Iridium is an element that is extremely rare on Earth's surface. Most of it sank deep into the planet's core when Earth first formed. But iridium is common in asteroids. When scientists measured the iridium levels in this global clay layer, they found concentrations up to 30 times higher than normal background levels. That spike told a clear story. This wasn't the result of slow geological processes. It wasn't volcanic activity building up over millions of years. It was the fingerprint of a sudden, catastrophic event. A single impact, a short moment in time. And yet its chemical signature has remained intact for 66 million years. Earth never forgot that day. The continents moved, mountains rose and eroded, oceans shifted and reshaped the planet's surface. But the chemistry stayed. That thin layer of clay became a timestamp, a permanent marker embedded in the planet's memory. This is one of the clearest examples we have of how geology records history. A brief event can leave a trace that lasts tens of millions of years if it alters the planet in the right way. Which brings us back to the question at the center of this story. If a single impact, lasting only moments, could leave a global chemical scar, what about something slower but sustained? What about an industrial civilization that burned fuel, released new elements into the air, and changed the composition of the atmosphere and oceans over thousands of years? It wouldn't need to leave craters. It wouldn't need monuments. It would only need to shift the chemistry. Because Earth has already shown us what it remembers best. At this point, it helps to introduce a careful idea from modern science. It's known as this Silurian hypothesis. Despite how it sounds, this is not a claim that an ancient civilization once ruled the Earth. It's not a rewritten history, and it's not evidence of lost cities buried underground. It's a scientific thought experiment. The question it asks is simple, but precise. If an industrial civilization had existed tens of millions of years ago, what traces, if any, could still be detected today? Notice what the question does not ask. It doesn't ask where their cities are. It doesn't ask what machines they built. And it doesn't ask whether their bones can be found. Because those expectations are based on a misunderstanding of deep time. As we've already seen, erosion wears surfaces down. Plate tectonics moves continents and recycles crust. Sedimentation buries and compresses what came before. Over millions of years, even the most durable structures are dismantled. Steel corrodes, concrete fractures. Biological remains are broken down, scattered, or transformed. So if a civilization existed far back in Earth's history, the absence of ruins wouldn't be surprising. It would be normal. This is where many discussions go wrong. We tend to search for objects, tools, buildings, artifacts, because that's how archaeology works on human timescales. But geology operates on a very different clock. It doesn't preserve stories, it preserves signals. That distinction is the heart of the Silurian hypothesis. Instead of asking what a past civilization built, it asks what that civilization changed. An industrial society doesn't just leave structures behind. It alters energy flows, it redistributes elements, it changes the composition of air, water, and soil. Those changes can be subtle, but when they occur on a global scale, they may leave traces that last far longer than cities ever could. This leads to the idea of chemical fingerprints. Not fingerprints in the human sense, but patterns that appear in the planet's chemistry. Things like shifts in isotope ratios, unusual elemental concentrations, global layers that don't match natural background processes. These are the kinds of signals geology is good at preserving. Importantly, science doesn't look for a single clue in isolation. It looks for patterns, repeating signals that appear across different locations and datasets. One strange measurement means little on its own, but consistent patterns spread across time and geography are how hypotheses begin to take shape. The Silurian hypothesis doesn't say such patterns exist. It asks what those patterns would look like if they did. That distinction matters. This is not about belief, it's about framing the question correctly. If we expect to find skyscrapers, we'll conclude that nothing came before us. But if we ask how an industrial civilization would affect a planet, chemically, climatically, and energetically, we open the door to testable ideas. And this is where the perspective shifts. The absence of evidence is not by itself evidence of absence when we've been searching for the wrong kind of evidence. Geology isn't a photo album. It's a record of processes. And if a past civilization ever existed, its legacy would be written not in stone walls, but in altered systems. That realization sets the direction for what comes next. Because if we can't look for ruins, we need to ask a better question. So if we can't look for ruins, what exactly should we look for instead? To understand what kind of evidence a past industrial civilization might leave behind, we need to look at one of the most reliable record-keeping systems on Earth: carbon. Carbon is everywhere in life. In plants, in animals, in fossil fuels. But not all carbon is the same. There are different forms, known as isotopes. The two most important for this story are carbon-12 and carbon-13. They behave almost identically in chemistry, but they differ slightly in mass. And that small difference matters. Living organisms tend to prefer carbon-12. It's lighter and easier for biological processes to work with. Over time, plants absorb carbon-12 from the atmosphere. Animals eat the plants, and when those organisms die, some of that carbon becomes buried. Under pressure and heat, over millions of years, that buried biological material turns into fossil fuels: coal, oil, natural gas. Because of their biological origin, fossil fuels are especially rich in carbon-12. Now consider what happens when large amounts of fossil carbon are burned. Carbon that was locked underground for millions of years is suddenly released back into the atmosphere. And because it's rich in carbon-12, it changes the balance between carbon-12 and carbon-13 in the air. This shift is not subtle. It's measurable, and the planet records it. Ice cores trap ancient air bubbles, preserving the chemical makeup of past atmospheres. Sedimentary rocks capture carbon from oceans and soils, locking isotope ratios into stone. Together, these records allow scientists to reconstruct changes in Earth's carbon cycle across deep time. This is done by measuring isotope ratios. Specifically, how much carbon-12 exists relative to carbon-13. When those ratios shift sharply, it signals that something unusual has happened to the global carbon system. This is not theoretical. These techniques are used today to study climate change, mass extinctions, and ancient volcanic events. They are among the most established tools in Earth science. And this brings us directly back to the Silurian hypothesis. If an industrial civilization had existed long before humanity, and if it burned large amounts of fossil carbon, it would have released carbon-12 into the atmosphere at scale. That release would not simply vanish. It would leave a distinct isotopic signature. Not a building, not a machine, a shift. And importantly, that shift would be global. Carbon moves quickly through the atmosphere and oceans. When its balance changes, the entire planet feels it. Which means geology doesn't need to find evidence in one place. It can find it everywhere. This is why carbon isotopes are so powerful. They don't tell us who burned the fuel, they don't tell us why. But they can tell us that something burned it. And this is the key point. Burning fossil fuels does not erase carbon. It relabels it. The carbon doesn't disappear. It changes form, changes location, and changes ratios. And those changes are exactly what rocks and ice are good at preserving. Once you understand this, the question shifts again. It's no longer whether a past civilization could leave evidence behind. It's whether Earth's deep history shows signs of large, unexplained carbon shifts that don't neatly fit known natural processes. And that leads us toward a much larger question. Have we ever seen something like that before? Have there been moments in Earth's past when the carbon record suddenly changed in ways that resemble what industrial activity does today? Because once you know how to read that signal, you start to notice where it appears. And once you notice it, you can't ignore what shows up 252 million years ago. 252 million years ago, life on Earth came close to ending entirely. This moment is known as the Permian-Triassic boundary, often called the Great Dying. It wasn't just another extinction event. Roughly 90% of marine species disappeared. On land, ecosystems collapsed. Food chains broke apart. Recovery took millions of years. By scale alone, this was the most severe biological crisis the planet has ever experienced. But what makes this event especially important for our story isn't only what died, it's what the rocks record. When scientists study sediment layers from this boundary, they see something striking. A dramatic shift in carbon isotope ratios. Specifically, a sharp drop in carbon-13 relative to carbon-12. In simple terms, the planet suddenly became flooded with carbon that looked biologically derived. Carbon-rich in carbon-12. This kind of shift doesn't happen quietly. It signals that enormous amounts of carbon entered the atmosphere and oceans in a relatively short time. When researchers first recognized this pattern, they asked the obvious scientific questions. Was this caused by massive volcanic eruptions? The Siberian traps released vast amounts of lava and gas during this period. Could methane have been released from frozen deposits? Methane is extremely rich in carbon-12 and can dramatically alter isotope ratios. Were there feedback loops between warming oceans, dying ecosystems, and the carbon cycle itself? All of these explanations remain under active study. None are dismissed. And that distinction matters. Science does not need a single cause to be correct. It needs evidence that matches physical processes, What matters here is not the explanation, but the pattern. Because the carbon isotope shift at the Permian-Triassic boundary looks uncomfortably familiar. When fossil fuels are burned at large scale, they release carbon-12-rich material into the atmosphere. The result is a rapid global shift in carbon isotope ratios. That's exactly the kind of signal we're seeing in modern records today. Now, to be clear, this does not mean that an ancient civilization caused the Great Dying. There is no claim of that here. What it does mean is that Earth's rocks contain at least one moment in deep time where the carbon system behaved in a way that resembles what large-scale industrial activity does to a planet. And that realization changes the conversation. Because earlier, we asked a theoretical question. If an industrial civilization existed millions of years ago, what kind of trace would it leave? Now we have something concrete to point to. A real, well-documented event. A massive global carbon disruption. Preserved in stone. This doesn't prove anything by itself. But it shows that the type of signal we would expect from large-scale carbon release is not hypothetical. It exists in Earth's history. And that's the payoff. The question is no longer, could such a signal survive for hundreds of millions of years? We already know the answer. Yes, it did. The harder question becomes something else entirely. How many of these events exist in the geological record? How well do we understand their causes? And could more than one process, natural or otherwise, produce similar signatures? This is where the Silurian hypothesis becomes useful again. Not as an answer, but as a lens. It tells us what to look for, and just as importantly, what not to assume. A civilization could disappear almost completely and still leave behind a detectable trace. Not in the form of ruins, not as artifacts, but as a planetary scale signal, a fingerprint written into stone, one that looks disturbingly familiar once you know how to read it. And carbon, as powerful as it is not the only thing industry leaves behind. But carbon isn't the only thing industry leaves behind. Carbon is one of the clearest signals a planet can record. But it isn't the only one. Because industry doesn't just change the air, it also produces solid residues, materials formed under temperatures and conditions that are rare in most natural environments. When you melt, refine, and process metals at scale, you create byproducts. Some of them are obvious: slag, ash, soot. Others are smaller, stranger, and easier to overlook. One example is metallic microspheres. These are tiny, round particles, often the size of grains of dust, formed when metal is heated to extreme temperatures, vaporizes, and then cools rapidly in the air. That rapid cooling pulls the material into a sphere, the same way a droplet of water becomes round as it falls. In the modern world, we produce microspheres in many ways. High-temperature furnaces, smelting, coal combustion, industrial welding and cutting. Even large-scale fires involving metal and synthetic material. The key idea is not that microspheres are proof of industry. It's that they represent a kind of residue that industry is especially good at creating. And unlike a building, residue doesn't need to stand upright to survive. It only needs to settle. Over time, tiny particles fall out of the atmosphere, wash into rivers, and end up in sediments. Once buried, sediments can become rock. And in some cases, those small particles can remain intact for very long periods. This is where the question becomes geological. If an industrial civilization existed in deep time, we would not expect to find their machines. But we might expect to find traces of their processes. the kind of high-temperature debris that a planet does not create easily without intense energy inputs. Metals are particularly interesting because many of them are relatively rare at Earth's surface. Certain elements tend to be concentrated in specific ores. They don't appear in large, evenly distributed amounts by accident. Industry changes that. Mining brings buried materials to the surface. Refining concentrates them. Combustion spreads fine particles over wide regions. In other words, industry doesn't just use metals, it redistributes them. If this happened at global scale over long periods, the planet might record it as unusual elemental patterns in sediments. Not as one isolated anomaly, but as repeating signals across layers. But here's where the scientific framing matters. Nature can also produce high-temperature particles. Volcanoes can generate ash and glassy fragments. Meteor impacts can create spherules. Lightning can fuse sand into glass. So the challenge is not imagining a signal. The challenge is distinguishing signals. In geology, almost nothing is convincing on its own. A single layer with odd particles could mean many things. A single deposit of unusual metal could be local geology. The real question is pattern. If you saw microspheres appearing in multiple locations in the same time window, paired with unusual elemental ratios and supported by other independent signals, then you would have something worth investigating. Not proof, not a conclusion, but a reason to ask better questions. This is why the Silurian hypothesis is careful. It doesn't claim that these markers exist. It says, if they did exist, this is the kind of evidence we would look for. Because industry doesn't vanish. It breaks down. Structures collapse. But debris persists. And debris doesn't need intent to survive. It doesn't need a story. It just needs time to settle into the Earth. Now imagine what it would mean to find the same kind of microscopic industrial residue repeating in deep time layers. Not once, not in a single place, but as a consistent fingerprint that appears again and again across the record. That would not tell us who made it, might not even tell us exactly how, but it would tell us something important. That high-temperature, planet-changing processes had occurred on a scale large enough to be written into stone. And then there's something even harder to erase. Up to this point, we've been talking about signals that are subtle, shifts in chemistry, tiny particles, patterns that require careful measurement. But there is one marker of modern civilization that is far more direct: plastic. Plastic is unusual because, before the industrial age, it simply did not exist in nature. There are no natural geological processes that produce synthetic polymers at scale. Every piece of plastic on Earth today is the result of industrial chemistry. That alone makes it significant. Plastic is also remarkably persistent. It doesn't behave like wood or metal. It doesn't rot in the usual way. It doesn't corrode into familiar minerals. Instead, it breaks apart. Over time, larger objects fragment into smaller ones. Microplastics, polymer fibers, tiny synthetic particles invisible to the eye. But breaking apart is not the same as disappearing. These fragments spread through soil, rivers, and oceans. They sink. They mix with sediments. They become buried. And once buried, sediments don't stay loose forever. They compress. They harden. They turn into rock. This is why plastic is often discussed as one of the clearest Anthropocene markers, materials that future geologists could use to identify our presence in the deep record. Not because plastic is dramatic, but because it's everywhere. It doesn't require a catastrophe to spread. It only requires time. From a geological perspective, Plastic behaves less like trash and more like a slow-moving sediment. Plastic doesn't disappear. It settles. Now imagine looking at this from far in the future. Millions of years from now, no cities remain, no machines, no recognizable tools. But layered sediments still exist. And inside those layers, a future geologist finds materials that do not fit natural chemistry. Synthetic polymers, unusual molecular structures, fragments that resist biological breakdown. They wouldn't need to know what an iPhone was. They wouldn't need to recognize a bottle or a bag. They would only need to see that these materials could not have formed without industrial processes. And this is the key point. We are not saying such evidence has been found in deep time. We are not claiming ancient plastics. What we are doing is clarifying what persistence looks like. If a past civilization developed synthetic materials, not necessarily plastics as we know them, but compounds with similar resistance to decay, those materials could outlast the civilization itself. Buildings collapse. Institutions fade. Knowledge disappears. But chemistry is stubborn. Once synthetic materials enter sediments at scale, they become part of the geological system. They don't need maintenance. They don't need meaning. They only need to be buried. This reframes the idea of a fossil. A fossil doesn't have to be a bone. It doesn't have to be a shell. In the deep future, a fossil could be a material, a chemical signature that marks a moment when a planet's surface chemistry changed. And this brings the idea uncomfortably close to the present. Because unlike rare metals or isotopic shifts, plastic is familiar. We use it every day. We discard it without thinking. Yet, it may be one of the longest-lasting signals we leave behind. Our trash may outlive our cities, not because it was important, but because it was everywhere. And once you see civilization this way, as a source of materials that spread, settle, and endure, it becomes harder to imagine a technological species leaving no trace at all. The question stops being whether evidence survives. The question becomes what kind of evidence is unavoidable. Because some technologies don't fade quietly into history. They embed themselves into the planet. But some technologies leave an even more unmistakable signature. So far, we've been talking about signals that are subtle: carbon ratios, synthetic materials, microscopic debris. But there is one category of evidence that behaves very differently: nuclear processes. Because when nuclear reactions occur, they don't just alter chemistry. They change isotopes in ways that are extraordinarily difficult to erase. And to understand why that matters, we need to look at one of the strangest discoveries in geology. About 2 billion years ago, in what is now Gabon, West Africa, something remarkable happened. A natural nuclear reactor turned on. This site is known as Oklo. At the time, Earth's uranium had a higher concentration of uranium-235, the isotope capable of sustaining nuclear fission. Groundwater flowed through uranium-rich rock, acting as a moderator, slowing neutrons just enough to allow fission reactions to occur. For hundreds of thousands of years, the rock at Oklo cycled through periods of nuclear activity. No engineers, no control rods, no containment vessels, just physics. What makes Oklo so important is not that nuclear reactions happened. It's how scientists discovered them. Decades ago, researchers noticed something odd. Certain uranium samples from the site were missing expected amounts of uranium-235. The ratios were wrong. Further investigation revealed isotopic patterns that could only be explained by sustained nuclear fission. The conclusion was unavoidable. nature itself had once run a nuclear reactor. And crucially, it left behind isotopic signatures that remain detectable for 2 billion years. This is one of the strongest lessons nuclear science teaches us. Nuclear processes leave shadows. They alter isotope ratios in precise, characteristic ways that do not resemble ordinary chemical reactions. And those alterations are extremely persistent. Even time struggles to erase them. This gives us something solid to stand on. We know, without speculation, that nuclear reactions leave unmistakable isotopic fingerprints. That's established science. Now, and only now, we can carefully take one step further. This next part must be clearly labeled. It is a hypothetical extension, not a claim. If a technological civilization were to use nuclear energy at scale, for power generation, for industry, or for weapons, it would also alter isotope ratios. Not in the same way as Oklo, not naturally, but distinct enough to stand out from background geology. Certain isotopes would appear in unusual proportions. Some decay products would persist for immense spans of time, and their distribution could reflect processes that don't match known natural patterns. The key idea is not that such evidence has been found. It hasn't. The key idea is that this is where science would look. Because nuclear signatures don't depend on buildings or machines. They don't require structures to survive. They exist at the atomic level, and atomic changes last. This sharply defines the boundary between what we know and what we are only imagining. We know that natural nuclear reactions can be detected billions of years later. We know that isotope ratios preserve those events with remarkable clarity. What we do not know is whether any past civilization ever produced such signatures, and we do not assume that it did. But the implication is important. If a civilization had used nuclear energy at scale in deep time, its absence from the record would itself require explanation, because energy, especially nuclear energy, is one of the most durable signals a planet can record. It doesn't fade quietly. It leaves a shadow. This raises the stakes of the question we're asking. Up to now, we've been dealing with signals that might blur the edges. Carbon cycles, synthetic materials, high-temperature residues. Nuclear processes are different. They draw a sharp line. They remind us that some forms of energy use are almost impossible to hide from geology. And that brings us to an even broader perspective. If energy can reshape isotope ratios for billions of years, if it can permanently alter the atomic makeup of rock, then the story isn't just about what civilizations build. It's about how they power themselves. And that leads us to a final, unavoidable question. And if energy can reshape geology, what about the atmosphere itself? Before we step any further, we need to ground ourselves in something certain. Earth's climate has never been stable. Across its long history, the planet has moved through ice ages and warm periods, greenhouse states and frozen worlds, often without any involvement from life at all. Volcanoes have altered the atmosphere. Continents have shifted ocean currents. The sun itself has changed over time. Climate change, in other words, is not new. What is new, at least in Earth's recent history, is the idea that a technological species might deliberately attempt to control it. Today we call that idea climate engineering or geoengineering. In modern terms, it refers to proposals designed to influence planetary systems, not to dominate them, but to keep them within survivable limits. This can take many forms. Injecting aerosols into the upper atmosphere to reflect a small fraction of incoming sunlight. Altering atmospheric composition to influence how heat is trapped or released. changing land or ocean chemistry to shift large-scale feedback loops. These ideas are controversial, largely untested, and carefully debated. But the concept itself is simple. If a civilization becomes powerful enough to significantly affect its planet unintentionally, it may eventually consider doing so intentionally. Now we need to be very clear. Everything that follows from this point is a speculative extension. There is no evidence that any past civilization engineered Earth's climate. There is no hidden discovery being suggested here. What we are doing is exploring what patterns such intervention would create if it ever occurred. Because science doesn't test intentions. It tests outcomes. From a planetary perspective, the reason for a climate change doesn't matter. A planet doesn't care why it's changing, only how. If a civilization attempted to stabilize or modify climate at scale, the planet would respond the same way it does to any forcing, through chemistry, through energy balance, through feedbacks recorded in rock, ice, and sediment. Aerosols, for example, would leave traces. Injected particles would eventually settle out of the atmosphere, becoming part of sediment layers. Their composition, distribution, and timing could differ from purely natural volcanic signatures. Changes in atmospheric gases would alter isotope ratios and leave signals in ice cores and ocean sediments. Once again, the key is not a single anomaly, it's pattern. Natural climate shifts tend to follow recognizable drivers: orbital cycles, volcanic pulses, tectonic rearrangements. A hypothetical engineered intervention might show different timing, duration, or distribution, not obviously artificial, but subtly unusual. And that subtlety matters, because the more advanced a civilization becomes, the less dramatic its planetary footprint may need to be. Early industry scars a planet loudly. Later intervention might aim for minimal disruption, just enough to stabilize, just enough to survive. From the outside, such a planet might not look broken. It might look carefully balanced. Again, this is not a claim. It's a boundary question. Could a technological species reach a point where survival depends not on expanding outward, but on managing the system it already inhabits? And if so, what would that management look like in the geological record? Science approaches this question cautiously, by comparing hypothetical patterns against known natural processes, by asking whether an observed signal can be explained by volcanism, by orbital forcing, by biology, before ever considering more exotic possibilities. Speculation is not an answer. It's a tool. Used carefully, it tells us where to look and how not to fool ourselves. Because there is a danger here. It's easy to mistake complexity for intention. It's easy to see design where only feedback exists. That's why this line must remain clear. We imagine possibilities, but we measure reality. Still, the idea changes how we see the planet. It invites a different perspective. Earth is not just a stage where events happen. It's a system that responds. Push it hard enough, and it pushes back. Whether change is natural or intentional, the result is the same. The atmosphere shifts, oceans adjust, life adapts, or doesn't. Intent fades, consequences remain, and that's the uncomfortable insight. From deep time's perspective, it doesn't matter whether climate change was accidental or deliberate. A planet records outcomes, not motives. Which leads us to a deeper question. If civilizations can influence climate, and climate leaves long-lasting planetary signatures, what else might a technological species change without leaving behind a single building or machine? And that leads to a deeper question. So far, We've been thinking about technology in familiar terms: energy, materials, chemistry. But there is one system on Earth that stores information more efficiently than metal, more persistently than plastic, and more precisely than stone: life itself. At the center of all life is DNA. DNA is a molecule built to do three remarkable things. It stores information, it copies that information with extraordinary accuracy, and it passes that information forward through time. Every organism alive today is carrying a biological record that stretches back billions of years. In that sense, DNA is not just the blueprint of life. It is a historical archive. Modern science has begun to recognize this. In laboratories today, researchers are actively exploring DNA data storage, using genetic material to encode digital information. The reason is simple. DNA is dense, stable, and capable of surviving far longer than most artificial media. Under the right conditions, genetic material can persist for tens of thousands of years, sometimes longer. That realization opens a carefully labeled question. This next step is speculative. It is not a claim. If a past civilization were technologically advanced enough to understand biology at a deep level, it might see life not just as something to study, but as something to work with. Not to dominate. Not necessarily to redesign entirely, but to guide. From a purely theoretical standpoint, biological systems offer a powerful medium. They self-repair, they reproduce, they spread. A small change, introduced early enough, can propagate across generations. If such intervention ever occurred, it wouldn't leave behind machines. It wouldn't leave factories or cities. It would leave patterns. For example, changes in the rate of evolution. Periods where new traits appear more abruptly than expected. Genetic features that spread rapidly across populations. Unusual bottlenecks followed by sudden diversification. To be clear, biology already has many mechanisms that can produce these effects naturally. Environmental pressure, mass extinctions, genetic drift. Science does not need an external explanation to understand evolution. But the Silurian-style question is different. It asks not why evolution happened, but what kind of traces would remain if biology itself had once been used as a technological tool. Unlike metals or plastics, life doesn't erode away. It adapts. It carries information forward, even as species change and environments shift. In that sense, biological traces could be more durable than almost any physical artifact. A building can collapse. A machine can corrode. But a genetic change, once established, can echo through deep time. Again, this is not a conclusion. There is no evidence that ancient civilizations engineered life on Earth. What we are doing is expanding our understanding of persistence. Technology does not have to be rigid to last. It can be soft, distributed, alive. And this reframes the entire idea of a legacy. A technological species might leave behind no monuments, no obvious ruins, no recognizable tools, yet still alter the trajectory of life itself. Not in ways that announce intention, but in ways that shape outcomes. From the planet's perspective, intent is invisible. Only results remain. DNA doesn't care who wrote it. It only cares that it can be copied. And once copied, information becomes history. This is why life is such a powerful archive. It records change not as an event, but as inheritance. And that makes it one of the hardest records to erase. As we move toward the end of this journey, the picture becomes clear. If a civilization existed before us, its most enduring traces would not look like relics. They would look like systems, chemistry, climate, energy flows, and possibly life itself. Which brings us to a final, unsettling thought. If information can live, if it can move from generation to generation without ever revealing its origin, where else might it hide? As we move deeper into speculation, one principle becomes increasingly important. The longer a technology is meant to last, the more it must resemble nature. Early tools are obvious. They stand out. They require maintenance. But over long time scales, the most durable systems are those that integrate rather than impose. This idea already exists in modern science. Some of the most advanced technologies we use today don't look like machines at all. They look like crystals. Crystalline structures have remarkable properties. They can store information. They can transmit signals. They can respond predictably to energy input. This is why crystals are central to modern electronics, from oscillators and lasers to sensors and quantum research. A crystal doesn't need moving parts. It doesn't need fuel. Its structure is its function. And once formed, that structure can persist for immense spans of time. Now, we need to be precise. What follows is an imaginative extension, not a scientific claim. There is no evidence that any past civilization built crystal-based planetary systems. But the idea itself raises a useful question. If a civilization reached a very high level of technological maturity, its goals might change. Instead of building larger machines, it might aim for stability. Instead of centralized systems, it might favor distributed ones. Systems without a single point of failure. Systems that don't announce themselves. Systems that quietly persist. From that perspective, planetary materials themselves become attractive. Crustal minerals, lattice structures, natural resonant systems, a distributed computational system embedded in geology rather than placed upon it, would not look like technology in the traditional sense. It wouldn't glow. It wouldn't move. It wouldn't broadcast. It would simply be. From the outside, it would look indistinguishable from rock. This is not as strange as it sounds. Modern computing already relies on materials whose function is invisible to the naked eye. The most important processes happen at scales far smaller than we can see. And as technology advances, complexity often becomes quieter, not louder. Again, this is not a claim about the past. It's a boundary thought. If a civilization wanted its technology to endure for millions of years, blending into geology would be an effective strategy, not by hiding, but by becoming part of the planet's natural systems. Such systems wouldn't leave debris. They wouldn't leave ruins. They wouldn't even leave obvious signals. Which is exactly the point. The most advanced machines might not look like machines at all. They might look like something we already accept as natural. This introduces a subtle twist in how we interpret the geological record. We tend to divide the world into two categories, natural and artificial. But over deep time, that distinction can blur. What begins as design can become environment. What begins as technology can become background. And once that happens, intent disappears. Only structure remains. To be clear, this does not mean that crystals or geological formations are secretly technological artifacts. Science demands evidence, and no such evidence exists. What this idea does is stretch our intuition. It reminds us that absence of obvious machinery does not automatically imply absence of intelligence, especially when timescales stretch into tens or hundreds of millions of years. A tool designed to last forever would not resemble a tool. It would resemble a law of nature. Quiet, stable, indifferent to attention. Technology doesn't need to shine to survive. It only needs to endure. And endurance often looks like simplicity. As we approach the end of this journey, the question shifts one last time. We've considered chemistry, materials, energy, life, and even the possibility that technology could dissolve into geology itself. But if something like that ever existed, something subtle, distributed, and long-lived, where would it leave the clearest trace? Not in what stands out, but in what cannot help but be recorded. And that is where we turn next. Up to now, every question we've asked has faced the same obstacle. Earth forgets. Its surface is restless. Mountains rise and fall. Oceans open and close. Crust is recycled, broken apart, and reshaped. Given enough time, almost everything on Earth disappears. But Earth is not the only place where history can be stored. Beyond the atmosphere, the rules change. Space is quiet, stable, and in many ways, far more patient. Unlike Earth, space does not erode surfaces with wind or water. There is no weather, no plate tectonics, no biological activity to break things down. Once an object is placed in orbit or left on an airless body, it can remain largely unchanged for millions, even billions of years. This is why scientists take the idea of space archaeology seriously, not as a search for aliens and not as a hunt for lost civilizations, but as a logical extension of how preservation works. If Earth constantly erases its past, where would time forget the slowest? The answer may not be on the ground beneath our feet. It may be above our heads. Consider the moon. The lunar surface has no atmosphere, no liquid water, no active geology on the scale we see on Earth. Impacts accumulate, dust settles, and then almost nothing happens. Some areas of the moon's surface have remained largely unchanged for billions of years. Anything placed there, tools, structures, debris, would not sink, rust, or rot. It would simply sit, preserved by stillness. Now expand that idea further. In space, there are regions of exceptional orbital stability, points where gravitational forces balance, known as Lagrange points. Objects placed near these regions can remain in stable positions with very little energy input. From a purely practical standpoint, these locations are ideal for long-term storage. They don't belong to Earth. They don't belong to deep space. They are quiet intersections in the gravitational landscape. If a technological civilization ever reached a stage where it left its home planet, even briefly, these would be logical places to leave equipment, markers, or infrastructure, not because of symbolism, but because of physics. Again, we need to be precise. There is no evidence that any ancient civilization placed objects in orbit or left artifacts on the moon. None has been found. None is claimed. What matters here is the direction of the question. Space archaeology doesn't ask, did this happen? It asks, if it did, where would the evidence survive longest? And the answer is clear. Not on a planet that constantly renews itself, but in environments that change as little as possible. This reframes the entire search for the past. Instead of digging deeper into Earth, it suggests looking outward, not for structures that stand out, but for anomalies that don't belong. Objects in unexpected orbits, materials that don't match natural processes, configurations that resist simple explanation, not obvious machines, not dramatic monuments, just quiet inconsistencies. From this perspective, space becomes more than a frontier. It becomes an archive, a place where time moves slowly enough to preserve what Earth cannot. This idea also shifts how we think about disappearance. A civilization doesn't need to vanish completely to leave Earth empty. It only needs to outgrow the planet. Even a short-lived presence beyond Earth could leave traces that last longer than everything that remained behind. Earth forgets. Space remembers. Not because it's designed to, but because nothing is there to interfere. And that realization brings a sense of calm. It means the past isn't necessarily lost. It may simply be stored somewhere quieter, somewhere colder, somewhere more still. As we widen our view, the story stops being only about Earth. It becomes about systems, about orbits, about where information can survive when planets cannot hold on to it. And as vast and silent as space is, there may be places even quieter. Places where time barely moves at all. And then there's a place even quieter than space. There is one place on Earth where time moves more slowly than almost anywhere else. The deep ocean floor. Far below the reach of sunlight, beyond storms and seasons, the seafloor exists in near constant darkness and cold. Temperatures change very little. Currents are weak, life is sparse, and most importantly, disturbance is rare. In the deepest ocean trenches, nothing happens quickly. Sediment settles from above at an almost unimaginable pace. In some regions, only a few millimeters accumulate over thousands of years. Layer by layer, the ocean quietly records time. Unlike the surface of continents, the deep seafloor is not reshaped by erosion. There is no wind, no rain, no freeze and thaw. Tectonic activity exists, but it is slow and localized. Once something reaches the abyssal plain or a trench, it tends to stay where it falls. This makes the deep ocean one of the most stable environments on Earth. From a geological perspective, it is a place of long memory. If large structures ever existed, not necessarily cities, but installations, platforms, or engineered foundations, the deep ocean would be among the few places where traces could persist the longest. Not because the ocean protects them, but because it barely touches them. Over time, structures would be buried, not destroyed, covered by sediment, pressed downward, locked into the seabed. This is why modern science takes the deep ocean seriously as a site of preservation, not as a treasure hunt, not as a claim, but as a logical conclusion about where change is slowest. Today, we map the seafloor using sonar and remote sensing. We see ridges, trenches, volcanic formations, and fault lines. Occasionally, we also see shapes that appear geometric: straight edges, right angles, symmetry. And here, science must be careful. Nature can produce geometry. Basalt columns form hexagons. Crystals grow in straight lines. Tectonic fractures create regular patterns. The human eye is very good at seeing intention where none exists. So every anomaly must be treated cautiously. The goal is not to label shapes as artificial. The goal is to understand what processes could create them naturally and what processes could not. This is why deep ocean research moves slowly. Every interpretation requires context. Every conclusion requires multiple lines of evidence. But the question remains valid. If something unusual were ever found, something too large, too regular, or too persistent to fit known geology, the deep ocean is one of the few places where it might still exist. Hidden not by secrecy, but by depth. What makes this idea powerful is not mystery. It's stillness. The deepest places on Earth are also the quietest. They don't erase, they accumulate. They don't break things apart. They cover them gently. Stillness preserves memory. And as the story descends here, everything we've discussed begins to align. Chemistry leaves traces. Energy leaves signatures. Life carries information. And when structures are placed where time barely moves, they may not vanish at all. They simply become part of the planet. From this perspective, the ocean is not a barrier. It is an archive. One that is vast, dark, and largely unexplored, which brings a subtle shift in how we think about loss. The past doesn't always disappear. Sometimes it sinks. And when it does, it enters a realm where disturbance fades, motion slows, and memory becomes layered beneath continents, beneath history, beneath noise. And beneath all of this, a familiar pattern begins to emerge. When we step back and look at everything together, a pattern begins to take shape. Not a story, not a timeline, a curve. It starts quietly. A civilization emerges with new ways to gather energy. It grows. It expands. It reshapes its environment to survive and to thrive. Energy use increases. Materials are extracted. Systems become more complex. At first, the changes are local, then regional. Eventually, they become planetary. This phase leaves signals. Carbon shifts. New materials appear. Unusual chemistry enters air, water, and soil. As long as energy is abundant and systems remain stable, growth continues. But over time, pressure builds. Resources strain. Feedback loops tighten. The environment responds. Climate shifts. Ecosystems destabilize. Margins narrow. This doesn't imply failure or error. It's simply what happens when energy flows through a finite system. Eventually, something changes. Growth slows. Systems reorganize. In some cases, collapse follows. Not always suddenly, not always completely. Sometimes the decline is gradual. Sometimes it is sharp. But the pattern remains. Expansion, pressure, adjustment, and then silence. What remains after that silence is not a civilization. It's a signature. Altered chemistry, redistributed materials, energy traces locked into geology. This pattern doesn't belong to humans alone. It doesn't require intention. It doesn't require intelligence. It only requires a system capable of growth and a planet capable of recording change. That's why this model feels uncomfortably universal. Carbon isotopes don't care who released them. Plastics don't care who molded them. Energy signatures don't care why they exist. Energy leaves a curve. History doesn't repeat because civilizations fail in the same way. It repeats because planets respond in the same way. And here's the quiet twist. A cycle is not a destiny. It's a description. Knowing the shape of a curve doesn't mean you're trapped on it. It means you can recognize where you are. Which brings us back to the present moment. Right now, humanity sits somewhere along that arc. We use vast amounts of energy. We alter climate. We create materials that will outlast us. These facts are not judgments. They are observations. The geological record is not a warning. It is a mirror. It shows us what happens when energy, matter, and time interact at scale. The difference, perhaps the only difference, is awareness. No previous civilization, hypothetical or otherwise, could look back at hundreds of millions of years of data and see the pattern clearly. We can't. That doesn't guarantee a different outcome, but it does create a possibility. Cycles describe tendencies, not inevitabilities. They tell us what usually happens when systems grow without reflection. They don't tell us what must happen when understanding enters the equation. And that understanding changes the meaning of the story. This was never about proving that others came before us. It was about learning how planets remember. Because when we understand what the Earth keeps, what it erases, and what it cannot help but record, we begin to see our own moment more clearly. Not as an ending, not as a beginning, but as a point on a curve that we are still shaping. Which brings us back to the present moment. We've traveled a long way tonight. Not across space, but across time. We moved through deep time, a scale so large that human history becomes a thin line, almost invisible against the age of the planet. We learned that Earth has memory. Not memory like ours, not stories or names or faces, but memory written into stone, into chemistry, into patterns that last far longer than any civilization. We saw how geology records change, how carbon leaves a signal, how materials settle and persist, how energy reshapes the planet in quiet, lasting ways. And we were careful. We separated what science can test from what remains speculative. We didn't try to prove that a civilization existed before us. That was never the goal. What we did instead was learn how to ask better questions. That distinction matters, because science doesn't move forward by chasing conclusions. It moves forward by refining how we look. If there is one thing to carry with you from this journey, it's this. The Earth remembers everything, but not in the way we expect. It doesn't keep cities. It doesn't preserve machines. It keeps changes. It keeps chemistry. It keeps energy. It keeps patterns. And those patterns last. Technology, no matter how advanced, leaves traces that outlive it, sometimes loudly, sometimes quietly. And whether a civilization lasts 10,000 years or 10 million, its present moment always becomes geology. That includes us. Right now, humanity is not standing outside history, looking in. We are inside it. Our actions today, the materials we use, the energy we release, the changes we make, are already becoming part of the planet's long record. Not as a judgment, not as a warning, just as a fact. Understanding that doesn't need to feel heavy. In fact, it can do the opposite. When you zoom out far enough, panic loses its grip. Deep time has seen ice-covered worlds and greenhouse worlds, mass extinctions and long recoveries, silence and abundance. And still, life continues. Civilizations rise, they change, they fade, and the planet keeps moving slowly, patiently, without urgency. That perspective doesn't make our lives smaller, it makes them lighter. It reminds us that we don't have to carry the weight of all history on our shoulders. We are participants, not the center. And that's a relief. So now, it's time to let the questions rest. You don't need to decide whether anyone came before us. You don't need to solve deep time or understand every pattern. Those questions can remain open. They can exist without answers. For tonight, what matters is simpler. You're here. You're breathing. You're safe. The room around you is quiet. The ground beneath you is steady. The planet is doing what it has always done, turning slowly through space, carrying oceans, continents, and countless lives along with it. Deep time is vast. History moves slowly, and whatever the Earth remembers, it remembers quietly. So allow your mind to release the journey. Let the scales collapse back down to the size of this moment, the sound of your breath, the stillness of the night, the calm that comes when nothing needs to be figured out. The universe is wide, time is deep, but tonight, you are safe.